Hello, and welcome to this lesson on standard form of a line. Please click the thumbs up if you find this video helpful, subscribe for more math help, and drop a comment and let me know what you think in the space below. Without further ado, we're going to jump into standard form by going back to what we already know about lines and equations of lines so that we can put standard form in the right context. So we already know something called slope-intercept form of line. And slope-intercept form of the line is named that way because it gives us the slope, which is the m value, and the y-intercept, which is the b value. And so when you're looking at y equals mx plus b, you can get these two pieces of key information very, very quickly off of the equation. It's also very useful for graphing because when we graph from slope-intercept form, we are able to simply plot the y-intercept and then count the rise over the run to get the slope, and that gives us our 2 points. So it's one of the most popular forms of equations of a line because it does give us that key information, and it is really easy to go from that into the graph. So what is standard form? Then we've got this form that we're already pretty happy with. Why another form? Well, standard form is simply a rearrangement of the same information, and it's sometimes called general form. So you might hear your teacher or a textbook or maybe another online video refer to standard form as general form. And I actually have seen different variations on this. I'm going to keep it to the one that I think is the most common, but we can talk about what other forms you might see or might go under the same heading. So it's pretty much an algebraic rearrangement of that information. It's rearranged this way: ax plus by equals c. And then whenever you're listening to a lesson or looking at notes, and you see that, and then you see the word where, okay? That's going to give you some important information about what you just read. So where a, b, and c are integers. So a, b, and c have to be integers for this to be standard form of line. And that introduces this other vocabulary where you might need to ask, what are integers? So it doesn't help you to read where a, b, and c are integers if you don't know what integers are. And so just to clarify, integers, which we've talked about before on this channel, are what we sometimes call the nice numbers, okay? And I'm listing some out there. Okay, so -4, -3, -2, -1, 0, 1, 2, 3, 4. And the dots there mean that that goes infinitely in both directions. So in other words, those are the kinds of numbers that we're looking for in front of the x and the y, or to be the coefficients of the x and y, as well as the number on the other side. So what are the pros of standard form? Well, one of the pros is that standard form can be used for all lines, including vertical ones. And we haven't at this point on this channel really gotten into why vertical lines are very, very different from all other kinds of lines. In fact, they belong in a whole different category, but they are lines, and you can use standard form to cover all types of lines, including vertical lines, which are different. One of the cons is that it does not easily give us specific information about the graph. So when you're first looking at it, you don't see anything about the graph. You can't just say, oh, this is what the y-intercept is, or this is what the slope is. Now you can get there from where you are, like from standard form, but it's not self-evident. And so graphing from standard form does require a little bit of work. Now, standard form is often seen in word problems and very specific kinds of word problems. So at the end of this lesson, we'll look at a situation where standard form would come out very naturally from the written description. Some certain written descriptions will lend themselves to slope-intercept form. For example, you pay a $20 flat fee for your international phone call card, and then it costs you $2 per minute. And we've looked at some problems like that very naturally go into slope-intercept form. There's other kinds of word problems that will very naturally go into standard form, which makes it useful to know. So how do we switch between forms? Pretty much this particular kind of skill in some areas of math is what we call multiple representations. And it essentially taps into your ability to take the same information and represent that information in different ways. So if you're given the information in slope-intercept form, can you rearrange that to get it into standard form, or vice versa, in order to access what you need or to be more convenient for like whatever the context problem is that you're working on? So the first thing I would do in this one, so we've got y equals negative 2/3 x plus 2. The first thing I notice is that my coefficient of x is not an integer. And so it's a fraction here. So I would like to get that to be an integer. Now, remember the reasoning here. So this is where I would tell my students, make sure that you have the volume up on the video, because you need to hear what I'm going to say. Otherwise, it's just a dot floating on the screen. That the fraction bar here is division. So this is negative 2 divided by 3. And I can undo division by multiplying. That gets into those core like operations that undo each other. So if I were to take this expression right here and multiply it by 3, okay, follow what's happening here. If you were to do the fractions out, 3 times negative 2 is negative 6. Negative 6 divided by 3 is negative 2. Or you could think of it this way. To take the negative 2, if you divide it by 3 and then multiply it by 3, the division and the multiplication will undo each other, leaving you with the negative 2. Now, here's where you need to be careful. You cannot just multiply one piece of an equation by 3. You've got to multiply everything by 3. Otherwise, you will mess up the equality of the equation. So if I'm going to multiply this little piece by 3, I need to make sure I multiply this by 3 and this by 3. All of it has to get multiplied by 3. Otherwise, it's no longer equal. Okay, so if you're going to multiply the entire left side by 3, you got to multiply the entire right side by 3. Everything's got to have that 3 in there. Once you do that, okay, you'll have 3y, and then we already established that those 3's will cancel each other out, giving you negative 2x, and then 2 times 3 is 6. And now to get this in standard form, I need this negative 2x to be over here on the other side. So I can't have the 2x, negative 2x on this side of the equation. So to undo negative 2x, I will add 2x to both sides. Okay, so that puts a positive 2x over there on the left. So I'll have 2x plus 3y. Negative 2x plus 2x is 0. And then I'm left with the 6. And now just notice that is now in the form ax plus by equals c, where a is 2, b is 3, and c is 6. Now, there are other ways you can do that. So some students would be very, very uncomfortable with how I did this right here. I added the 2x here. And so they might do this. Okay, so we're sitting here. And you're okay with the adding of the 2x, but when you add the 2x, it ends up on that side, okay, which is totally fine. But remember, the form has the x coming first. And so at this point, you would need to use what's called the commutative property of addition, which essentially says this, like 4 plus 5 is the same as 5 plus 4. In other words, the order that you add something does not matter. And then you could change it from there. Okay, so if what I did bothers you, especially with the placement of the plus sign, because I had the plus sign out here and then it looked like it moved to the other side of the 2x, and you're like, I don't know what she did with the plus sign there. Okay, that's what I did with the plus sign. So if it helps you to work it out this way, please do it that way. And eventually you'll get comfortable with what I did. All right, now this one has a decimal in it. And again, we have to have it in integer form. So there's a couple of ways you can reason through this. One is to think of 0.3 as 3/10. Okay, if you were to read that out loud the proper way, which we do when we're in elementary school, and then we just kind of stop doing it. We say it's 0.3, and that's how I say it. That's how all my students say it, like 0.3 or 0.3. But if you ask me what is the proper value of that, I would say that is 3/10. Okay, and once you change it to the 3/10, now you're looking at a problem similar to what we just did, where you can now clear the denominator by multiplying everything by the denominator. You clear it out, okay, multiply by 10. You could also reason that out by thinking in terms of moving the decimal point. And if you multiply or divide by powers of 10, you essentially move the decimal point. That has to do with the fact that we have base 10 numbers, which is kind of a cool concept, but one not for this video. I teach an electronics class where we do base 2 numbers. And so you might know that if you take 0.3 and multiply it by 10, you're going to move the decimal point 1 digit to the right, and that would get you the 3. But the same rules apply. You can't just multiply one piece of it by 10, okay? If you multiply the left-hand side by 10, you have to multiply, or the right-hand side by 10, you have to multiply the left-hand side by 10. But on the left side, we're multiplying the entire side. Like the y is the entire side. It's getting multiplied by 10. On the right, I'm only multiplying part of it by 10. So I've got to make sure that I multiply all of it by 10. So that gives me 10y equals 3x minus 20. And this time we'll be subtracting the 3x from both sides. Now, this is where adding a negative might be a good way to think of it, because when I go to do the subtraction on the left side, sometimes like the negative students are like, I don't know what to do with the subtraction sign. So in this one, instead of writing it as minus, I'm going to say plus negative 3x. And what that's going to do is allow my left side to emphasize that what we've got there is a negative 3x. 3x plus negative 3x is 0, leaving me with a negative 20. And now I can use the commutative property to switch the order of that and make sure everything is in the right order. So A is negative 3, B is 10, and C is the negative 20. Now, what I would normally do on that, just so you can see what I would do if I wasn't trying to explain it, is I would, in my head, I would just say minus 3x, and then write it like this, remembering that the minusing of the 3x means that the minus sign is attached to the 3x, making it a negative 3x. And then this would be a plus sign there because the 10y was positive to begin with. But I have had students really mess up the pluses and the negatives there. So it's just one of those things, like just be careful of, and just remember that when you're subtracting the 3x from both sides, it's going to make the 3x negative on the other side of the equation. All right, so that was our second example. Now, this one is an example that's in standard form, okay, and we're going to take this from standard form to slope-intercept form, okay? And that's probably the more common direction that you will end up doing this. Like you'll end up with an equation in standard form and you'll need to put it into slope-intercept form. So to do that, we essentially need to solve for y. Okay, so I'm going to take a look at like the y. Oh, there it is. There's my y. It doesn't want to highlight correctly. There we go. And so we want to get the y by itself. Now, if you look at what's done to the y is being multiplied by 5. And we're also adding in a negative 2x, okay? And those things are being done. Now, if this is very uncomfortable for you, there is a video on literal equations that I encourage you to go back and look. It'll be in the Algebra 1 playlist, and it'll be titled Literal Equations. So go and find that video. If I can remember to link it in the description box, I will do that. So you can check out the description box first, and then if you can't find it there, go look in the playlist. But I go through in detail the mechanics of this, which I'm not going to do at this time because it's assumed that we've already done it. To get the y by itself, we will first add 2x to both sides. And so negative 2x plus 2x is 2x, leaving me with 5y. And then over here, I will have 2x plus 15. Now, some of you might be saying, well, wait a minute. If you were adding the 2x, shouldn't it look like this? Like 15 plus 2x? Well, like, yes. But again, remember, we're trying to get it into slope-intercept form. So we probably want to engage the commutative property again that says I can add numbers in either order, and I'm just going to put the 2x out front, not because it's more correct, but because that's the position I want it in for slope-intercept form. Now we will divide everything by 5. If I divide everything on the left by 5, which I have, okay, I have to divide everything on the right by 5 in order to keep them equal. 5 divided by 5 is 1, leaving me with y. The slope of this line will be 2/5 x, and then 15 divided by 5 is 3. And now I've got it into slope-intercept form, which would be convenient for graphing. All right, so where might we see standard form? Okay, and I mentioned earlier that we would get to this where there are certain word problems where they just lend themselves to standard form. So here's one word problem. You are planning a party and need to buy balloons and streamers for your party. Balloons cost 25 cents each and streamers are $1.50 per pack. Your budget is $20. Write an equation for the number of balloons and streamer packs you can buy for $20. Okay, now I'm going to use B for balloon. Okay, I want to make sure that I don't make it look like a 6, so I'm going to use a capital B. And S's are tricky because S's can really look like 5s. So I'm going to do my best with the S to make sure it looks like an S and not a 5. Okay. But the expression for that would be 25 cents times the number of balloons. Okay. So you're paying 25 cents per balloon. So 25 cents times the number of balloons. Added to that, $1.50 times the number of streamer packs. Okay, really trying to make my S look like an S there. That's how much you're spending, and all of that needs to equal $20. That's your budget. So the cost of the balloon times the number of balloons plus the cost of the streamers times the number of streamers has to equal 20. Now, in reality, nobody is going to make sure you come out to exactly $20. In fact, that might not even be possible to come out to exactly $20. In reality, this would be like a less than or equal to problem, and we haven't addressed that. That's going to be coming up next, is like, what do you do if you have a less than? But for now, the goal of this is just to see, yeah, there are situations where standard form is the form that just kind of dumps out of the description. And so usually be where you've got two things, often they cost two different amounts, and you need to find some way to like balance out how many balloons, how many streamers. And a lot of times they'll come with another piece of information that would help you figure out how many balloons and how many streamers should you get. Okay, but I wanted you to see the kind of word problem that is used there. All right, that's it. Don't forget, check out the practice set linked in the description box. I do a practice set for all of the lessons so that you can practice what we've covered in the lesson. Give this video a like and subscribe for more math help, and drop me a question or comment below and let me know what you think. I will see you in the next one.